Okay, well, let's get on to the material today. Remember how we left this off last time? What did we talk about? Well, introduce this new device that you can introduce into your circuit modeling repertoire called the transmission line. And we drew it like this. Two bars, and that 2 bars we learned could take on a number of physical realizations in the real world, right? You could have coaxial cables where you had an inner conductor and an outer conductor, which represented 2 conductive bars that a signal can travel down. You could have a variety of different structures on printed circuit boards, and we passed around some examples of that. And there are also things like twisted pair, the wires on the big utility poles that are used to transmit high voltage are forms of transmission lines. In that case, the top bars, they're actually 3-phase, so there's 3 transmission lines kind of tied into one another. The ground is often used as the bottom bar, and then the top wires are like the top bars. So this is sort of our system. And just to introduce some terminology here, in this class, we're always going to have a load side where we hook some stuff to it, and then a source side, V sub S voltage, and then all realistic sources have some sort of impedance R sub S, resistance R sub S. So we'll call it source side, load side. Sometimes you'll call this the generator side, and that's actually an artifact from power, because that's where you put your generator to excite, your city, which is on the other side of the transmission line, acting like a giant resistor, sucking up power. So you'll see sometimes this expressed as V sub G or R sub G in notes and books. Well, I'll typically use R sub S to denote source side resistance, and V sub S to denote a source side voltage source. And this transmission line, we found, obeyed the telegrapher's equations. You just need to know the length, D, the impedance Z naught, the velocity of propagation V sub P. And if you know those things, you pretty much have the model, the physical model, which was that system of differential equations that describe voltages and currents on this device. So that impedance is the ratio of voltage to current that device transmits. It's not a resistor in the sense that it's wasting energy or burning up energy and electrical power. It's actually just a parameter of transport that happens to have the unit of ohms. And we mentioned last time, we kind of insinuated this, and we're going to explore this in detail today. What happens when you have this device that transmits voltage and current at one ratio Z naught, and that waveform gets to the end of it and it encounters a device that accepts voltage and current at a different ratio? Well, what happens, and we alluded to this last time, is that you have to spawn a reflected wave to match the boundary conditions. So that's really what we're going to talk about today. And what it'll allow us to do is to trace out the transient waveform that travels on this transmission line as it excites and charges up, we say. Because remember, this transmission line is really just a bunch of intertwined capacitors and inductors. Series inductors, shunt capacitors. And I've drawn them as discrete components, but we know that it would actually take, to model this perfectly, an infinite number of these intertwined, which is why we have to resort to that partial differential equation. But if you think about it, if you leave this connected to a DC source for a long time, what's going to happen? All the capacitances are going to charge up. All of the inductors are going to turn into short circuits. And if you wait long enough, this system should just look like 2 lines, which is what we're familiar with modeling conductive paths as. But it's really the transient to get to that point that's really interesting and affects things like high-speed digital logic and communication signals and that sort of thing. So that's the effect that we want to capture today in our analysis. So let's go ahead and start off. I'm going to assume that at t equals to 0, I start off with a transmission line that doesn't have any of those capacitors or inductors charged up. There are no voltages and currents going on that line. We call it a dead line. And I am going to flip the switch. This is going to be a DC source. And I'm going to flip this switch at time equals to 0, and we're going to trace out what is the transient on this circuit. Now, remember the general solution for the voltage and the current on this line. Voltage, as a function of space and time, is equal to an amplitude V+. That's the amplitude of the forward traveling wave. It's going to have some functional shape to it, f of t, and we're going to put a minus z over velocity of propagation, because this term here denotes a wave traveling at constant velocity v sub p in the positive z direction. Always travels opposite of what this sign is. So when we go to write the backwards traveling wave, its mathematical form, give it a different amplitude, g of t plus z velocity of propagation. And of course, I has a very similar form, the accompanying current waveform. Remember, this is an I on the top bar and the bottom bar at any given moment in time and space. Okay, so at the terminals of this, right here, oh yes?
They're on the bottom, but next to the D and IST or ZT. No, in the diagram.
Oh, in the diagram.
Next to the D.
Next to the D. This.
IS?
No, this would be I, because this return current is defined in that direction.
Okay.
Right there. And the sort of the we made a discussion that, and there's also like displacement current, even though there's no physical charges. There's a change in the electric field across this capacitance here, which we call current as well, to make Kirchhoff's current law work out. Now, it could be that this V plus term would be negative in amplitude, and if in that case they both flip. So this one's going this way on the bottom bar, this one's going this way on the top, they flip if that's negative. But they're always together in that form when they travel on the line. It takes a little getting used to. So we have a V source here, and we're also going to talk about a V load in short order. Let's concentrate on that V source. V source, if I wanted to model it, would look like, well, I'm going to use a unit step function. V naught unit step function. T. Right? Unit step is 0 when t is less than 0, and 1 for t greater than 0. So it provides a nice little gate that matches the mathematical structure of this signal. Okay, so at z equals to 0, this is basically going to be a unit step function. So this kind of, in a way, gives me the form of my voltage, and as a matter of fact, the current that's going to be on this system. So for t greater than 0, my voltage as a function of space and time is equal to V naught unit step, and I just plot my argument t minus z over velocity of propagation into my unit step function. Now I have a traveling wave that's going to be the leading edge of a DC pulse that goes in the positive z direction down the transmission line. I don't have to worry about a backwards traveling wave, because as a part of this problem I said this was an uncharged line. There are no voltages and currents on this line. I made a change to one side of that line, the generator side. It's going to take a significant amount of time to even see a backwards traveling wave. What is going to have to happen is enough time is going to have to elapse for that leading edge of the waveform to make it all the way down to the end of the line, possibly spawn a reflection if the line is mismatched, and then start sending a traveling wave backwards. So in fact, what I should say is that between capital T and 0 time, this solution will be valid. Capital T is really just distance over the velocity of propagation, meters over meters per second. That gives you a value in seconds that tells you how long it takes the signal to get from one end of the line to the other end of the line. And in fact, that has a special word that we'll be using called the transit time. And it's really just, there's no need to derive it, right? It's just velocity is equal to distance, distance is equal to velocity times time. Just rearranging that basic equation from physics. So our current, by extension, we have all the information we need to write the current waveform, which again will just be a forward traveling wave. And that's our solution for that time interval there. Yes?
Question?
VO.
And then it says U?
U, yeah, unit step function.
Oh, gotcha.
One other thing I should note here, too, is we can actually solve for V naught if we're given numerical values for what's attached to this thing, right? Because it's a dead line, they put the dead line model for a transmission line. I've got this transmission line, and at various stages in our analysis, we're going to replace our transmission line with equivalent circuits. You know how you have like a Thevenin equivalent? We're going to do Thevenin equivalents for transmission lines. It's a little trickier because the transmission lines are two-port devices, so we got to come up with a Thevenin equivalent for the left side and the right side, or something equivalent like that. And what's more, the equivalent that we use is going to depend on the state of the transmission line. I'll give you the equivalent circuit that we're going to use for the simplest state of the transmission line, which is the discharge state. Remember, there are no voltages and currents on this device as we started out. It is a dead device. The only thing you can do is dump some voltage and current in one side and have it propagate the waveform down at a certain ratio, or the other side and have it propagate the voltage and current down the transmission line in the other direction. So here's a great equivalent circuit model if you want to figure out how this interfaces with the rest of the elements. So basically, if you see this in a circuit diagram, and I tell you that it's a dead line, completely discharged, until it starts to charge up, you can replace it with this equivalent circuit model. And so in the problem that I've showed you up here, Vs is a DC source. It is now at time greater than 0 switched into the transmission line. So now the left side of that line looks like a voltage divider, and my V naught winds up being whatever voltage division occurs across here. I can use my voltage divider equation, V sub S times Z naught over RS plus Z naught. Everybody understand how we got to this? Pretty simple. Device can only accept things with this voltage and current with this ratio. So when you first hook it up, that's what it's going to look like. 2 Z naughts stuck on the end. The other side of the thing we can also model. We can put the other terminal, but it's not doing much, so it's kind of boring. It's just a resistor connected to a load resistor. It's a dead circuit. So we're not going to get any voltage out there until one transit time has elapsed and that voltage makes it towards the end. Okay, so now let's look at what happens at the end of the line. If we go back to this diagram here, we see that when we put z equals 0 in and I equals z equals 0 here as well, this doesn't exist. This is a unit step function that collapses to a unit step t, and you get the voltage at the front of the line. What happens now when we observe this at the end of the line? And that's what I'm going to put is voltage and current evaluated at the end of the line with our unit step functions. So let's do that. At the end of the line, for z equals to d, voltage as a function of space and time is going to be equal to v naught unit step t minus, I'm going to make z the end of the line, so this is going to be d over vp. And now I have the potential, because I've gotten to the end and could possibly be spawning a reflection, I'm going to just put this in generic terms. I've got my general solution, v minus some function that I don't know what it is yet, but I'm going to guess, t plus the end of the line over vp. And likewise, I have the same expression for my current equation. But basically what I've done here is taken the general solution, which has the forward propagating wave in it. I've evaluated it at the end of the line, but I haven't made any a priori assumptions about how big or what shape the reflected wave is going to take. We're going to derive that. And it actually makes a lot of sense when you see the result. We won't ever have to derive it again. But does this make sense? Yeah, u of t minus d over velocity of propagation. At the end of the line, I am not going to see any waveform until the argument of this unit step function is positive. T is going to have to be at least d over velocity of propagation to turn that on. And that's a transit time. So really, t has to be greater than a transit time for this thing to turn on. Makes sense. Okay. Now, this is where we get to the fun part. We have a boundary condition to enforce at the end of that line. The boundary condition states, and this is common in electromagnetics and all of circuit theory, you cannot have discontinuities in voltage and current across a boundary. So when I look at the end of that line, this voltage evaluated for z equals to d, and this current evaluated for z equals to d, this had better be the voltage and current coming into and out of the line. In other words, if I measure the total voltage over here on the line and just move a tiny infinitesimal amount to this side over here, that had better be the same voltage. So my load voltage, and likewise whatever load current is in total is coming out here and going into there, that had better be the total load current traveling through my resistor at that point. Make sense? And so that allows me to enforce a boundary condition. Voltage evaluated at the end of the line as a function of time divided by current evaluated at the end of the line as a function of time should be equal to total voltage V sub L over I sub L. And we have stuck on the end of this device another device that only accepts voltage and current in a certain ratio. We call that R sub L, the resistance of that device. And so if we expand out, what we get is V naught unit step t minus d over velocity of propagation plus v minus g of t plus d over velocity of propagation. Times this mess of mathematics in the denominator that's very straightforward. I'm just taking these two things and dividing them by one another. And out of this analysis, we're going to come up with some really useful results that will take us through the rest of our analysis of time domain transmission lines. So now let me rearrange that equation that I just wrote up on the board, and we'll be able to glean some interesting results from it. So the key result here, if I rearrange stuff, that V plus, which I called V naught over there, I'm going to call it V plus, the forward propagating wave. So we're going to use it in the generic sense in a second. Times that unit step function, U of t minus d over velocity of propagation, times the value, when I rearrange it, 1 minus RL over Z naught is equal to minus 1 plus RL over Z naught times V minus times G t plus d over velocity of propagation. This is just that previous equation rearranged, putting the u on one side and the g on the other side with some constants in between. Now, believe it or not, it was a lot of work to get here algebraically, but you can tell a lot about what's going to happen at the reflection interface just from this relationship here. Notice that this and this and this and this are all constants. The only functional dependence of time is this and this. We don't even know what this is, but because there's a functional dependence of time on this side, this had better match, because this is the only time dependence that can kind of counterbalance the equation. So we can automatically write g of t plus velocity of propagation must be a unit step function. So by adding in this offset, what I can really get is g of t is the unit step function t minus twice d over velocity of propagation. Which means when I put it into my transmission line equation, for t greater than 1 transit time, the shape of my waveform will look like this. Okay, put down your pencils and let's make sense of this. We've been doing a lot of math. What does this physically mean? This means that if this boundary condition is to be enforced, we are going to have a unit step function that propagates in the opposite direction, in the minus z direction. That's what plus z over vp means in this expression. And there's going to be an offset in time. This is not going to turn on until t greater than capital T, transit time. So in other words, if t is d over velocity of propagation, and I'm evaluating this voltage at the end of the line where z equals d, then the waveform is going to turn on. That's when you see it at the end of the line, and it starts to propagate backwards. 1 transit time after you put the signal on the line, it's going to show up at the end and spawn a reflection. How much time is going to elapse in order to see this thing strike the source side again? 2t, 2 transit times. 2 distances divided by the velocity of propagation. ultimately, keeping track of these problems becomes like a tennis match, right? It's just like you just watch it go back and forth and back and forth. I didn't bring them down today, but I'll bring in some animations to kind of show what some of these pulses actually look like, to bring to life some of our boring, dry analysis in mathematics. But really, it comes down to just a tennis match. This constant velocity signal going back and forth and back and forth and back and forth. And that's what this physically means. It's a nice result, though, because what it really means is that regardless of what I hook at the end, if I just take a resistor and I hook it at the end, regardless of what the value of that resistance is, the thing that reflects back is going to have the same shape as the thing that I sent down the line. In other words, if I send a square pulse down the line, I'm going to get a square pulse back. If I send a sinusoid down the line, I'm going to get a reflected sine wave. The shape is always the same if there's a resistor. The only time you get a different shape is if you start putting reactive elements or nonlinear elements on there. So that's good. That's comforting.
Dr. Durgan?
Yeah, sure.
This is Bill in Savannah. I've got a question about, you changed the V naught to V plus. Mm-hmm. Just to make your life difficult. No, I'm kidding. They're interchangeable. The reason why I made this back to a V plus is because of the next thing that I'm going to put on board. Remember, I said there were two things that we can glean from this relationship. One is that the shape of the pulse is the same as what you sent down. Whatever reflects back is going to be the same shape as what you send down. If you send down a square wave, you're not going to get a triangle wave reflecting back if there's just a resistive termination. And then to your point, Bill, I switched it back to V plus because I was being a little bit sneaky. I want to derive a general formula for all transmission lines based on this one result. So I'm going to leave V plus in there for the moment, and you'll see why this is useful. In fact, okay, we now know that these two functions are the same. So I'll just cut to the chase here. So they're going to be equal. They could drop out. And then what I'm going to do here is I'm going to rearrange this equation and divide through. I'm going to divide V plus into that side and this swag into that side. And what I've got left over is a ratio of V minus to V plus. And it turns out, so now I said all the shapes of the waveforms that we send down are the same reflected back when I got a resistive termination. Now we're going to figure out how big the waveform is. What is the amplitude of the waveform? And if I rearrange this, what I find is that ratio of reflected wave amplitude to incident wave amplitude is the following relationship. And this is so important in this class and in electromagnetics in general that it gets its own variable, its own capital Greek variable. That's how you know it's important. Capital Greek is coming. Capital gamma. Capital gamma. This is the reflection coefficient of our transmission line. Pretty snazzy. When is the reflection coefficient 0 on a transmission line? When you look at that expression, what would make that 0? Yeah, exactly. RL is equal to 0. RL is equal to Z naught. Then the numerator is equal to 0. We call that the matched condition. In fact, that is usually what you're trying to achieve when you are designing your own transmission line, when you're trying to pick the trace width and PCB thickness to figure out how to connect your two devices on surface mount components. You're trying to match them. That's the best case scenario, because that means you won't have any reflections on your line. What you see is what you get. You send a pulse down, you'll get a pulse at the backside, and there won't be any reflected energy. Doesn't always happen. So a lot of times you have a mismatched load. And there are several different values. The first thing to note
with this reflection coefficient is that the magnitude for a passive positive resistance is always going to be less than or equal to 1. Right? If these are all positive numbers, my Z0, my RL, then the ratio of RL minus Z0 to RL plus Z0 is never greater than magnitude 1. It can be equal to positive 1. Under what scenario would that happen? What kind of load is a positive 1 reflection coefficient? No, that's a negative 1. Yeah, exactly. When RL is infinite. In other words, when my transmission line is terminated with an open circuit. In fact, if I had a system like this, let's say I had a source resistance that was matched and a transmission line that was terminated with nothing, an open circuit. Interestingly, the dynamics of this system, you're very familiar with open circuits, right? You know that all the voltage basically pops across them. But you probably never understood what the physical transient was for that open circuit. If you close the switch on this system, let's say you've got a 12-volt source. As soon as I close the switch, this looks like a Z0 impedance because it's a dead discharged line. My voltage divider says initially there will be 6 volts traveling down the line, right? Half of it goes across this source impedance, half of it across the dead impedance Z0 of the transmission line. I can only use that equivalent circuit model for a little bit. When it starts to charge up, it's no good after that. But for at least 2 transit times, I can call this a Z0 on this side of the circuit. When the reflection comes back, then it's something different. But okay, so I got 6 volts traveling down the transmission line. It gets to the end here, and I think, oh, I'm going to have a reflection. How much reflection? Well, I got infinity as my load. Infinity over infinity minus whatever is going to be positive 1. So that means there's a 6-volt reflection coming back. Which means, initially, if I had a bunch of voltmeters connected to here, and I was looking over time at the traveling waveform, I would see the 6-volt waveform traveling down, down, down. It would get to the end, and lo and behold, it would double up. And I would see 6 more volts. So this part would be 12 volts in total, and there would be a stair step. The step would move with constant velocity to here. And it turns out, we haven't talked about it yet, but this source is conveniently matched to the impedance of the line, so there's no reflection on this point. And what do I have? 12 volts all the way across the line to this point. And at that point, it looks exactly like the circuit problem that you're used to solving. What happens when you have an open circuit with a 12-volt source? Oh, you get 12 volts across the open circuit. Believe it or not, though, it takes a non-zero amount of time to get to that point. You never knew that weird stair-step transient was happening in your 2 wires that emptied in space, but that's what happened. That's what's physically happening. So what's the other way to reflect all of the voltage in this scenario? To get a 100% voltage reflection coefficient. 0, short circuit. Exactly right. Well, what happens in the short circuit case? I short this. Otherwise, the same thing happens. I connect this. 6 volts starts traveling down the line with constant velocity. After 1 transit time, it strikes the end. What is the reflection coefficient? Well, now it's 0 minus Z0 over 0 plus Z0. That is negative 1. So again, 100% of the voltage reflects at the end of that short-circuited line. But it's within a phase change. And that's absolutely critical, because you'll get the complete wrong answer if you don't get the phase change. You'll get the open circuit case. What happens now is that a negative 6-volt waveform travels down. And what is negative 6 added to the 6 that's already there? Nothing. So interestingly, if you had a whole bunch of scope probes connected along in sequence and kind of looked at the spatial evolution of this voltage and current waveform, the voltage waveform would travel down with constant velocity, and then it would slowly erase itself until it got to the end, and then the negative 6 volts would see a matched source side, and all reflections would stop. Hey, you probably didn't know that was going to happen either, right? At that point, now it looks exactly like all the circuit problems that you're used to doing. If you took a source and took 2 wires and then tied them at the end like they were a short circuit, you'd flip the switch and you'd see no voltage across the end of the line. In fact, you'd see no voltage across the entire line. You could never measure a voltage drop. Well, that's exactly what the transmission line model is predicting, but it says there's a really weird transient to get to that state, a wave that goes down and then erases itself. It takes 2 transit times. And the thing is, if you've just got wires in your your 3041 lab, is that where you do circuits? If you just have your 2 wires and you tie them together, and you would literally have to be observing on the nanosecond scale or lower to see that transient. None of that cheap equipment that we have in that laboratory could possibly do that, so don't try that. However, this becomes very important if you've got high-speed digital logic and things that are clocking in the gigahertz regime, where that is a time scale at which this phenomenon is very important. So interesting. Making a waveform, then erasing it. And this brings me up to the second equivalent circuit model that I would like to introduce. So we have nothing is on the line and we just connected something to it model. It looks like 2 Z0 resistors on either side, 2 dead resistors. When a transmission line has been connected to DC circuitry for a long time, and that qualifier for a long time in this class means lots of transit times have happened and all the reflections are done. If it has been sitting there for a long time, then the equivalent circuit model that we use is just 2 wires. The model that you're really used to using in 3040 class or 2040. So whether there's a short, an open, or a resistor, this is the circuit model that you can use for the case where a DC source is connected for a while, a long time. That while may be a few nanoseconds based on the frequencies and the size of your circuits. If you're doing really low frequency stuff, or well, it doesn't matter if it's low frequency or not. If it's a small circuit, that's on the order of nanoseconds. If it's a large circuit, it could be on the order of microseconds or larger, and then it becomes important based on the frequency scale that you're looking at. Any questions so far? Notice that you can get any value in between -1 and +1. Generally speaking, if the load resistor, whatever you put here, R sub L, is less than Z0, then you're going to get a negative reflection coefficient. A portion of that voltage waveform is going to reflect back and it's going to flip in sign. If you've got an R sub L, a load that's larger than Z0, then you usually get a positive reflection coefficient, and there's usually a doubling up of voltage. That tends to freak students out because, like, you think, oh, I get like 6 volts coming down, maybe I connect a non-infinite resistor there, and I get positive 4 volts coming back. That freaks people out because that means at the end of the line, there's 10 volts, and I only put 6 at the front of the line. Does that seem illegal? Dirty, almost? I don't know. That doesn't seem right. But it's okay. It's okay. Conservation of power always holds in a transmission line. Now, there's no such thing as conservation of voltage. You can double up temporarily the voltage in a transient. But in the end, this is the model that you use to describe the steady state behavior, and everything will kind of behave like normal once you do that. But you can get, for a short period of time, more voltage at the end than what you're actually sending down the line. And that makes sense, right? Because if we think about conservation of power, when does that happen? When my load resistance is larger than Z naught. The product of voltage and current traveling down the line, we know that voltage times current is watts. That's the power carried by the line. If I double up my voltage, I may double up my voltage on a load, but remember, my current draw for a big resistor is much less. And so if you actually worked out and looked at the V times I across the resistor and compared it to the V times I on the line, V times I on the resistor is always less than or equal to the V times I, the power carried down by the line. The voltages can do whatever they want. They're just there to satisfy boundary conditions. They're not necessarily conserved. They're conserved across the boundary, but you can get doubling up on what you're feeding a resistor, despite the fact that you put in less traveling down the line. I'll show you an example where that actually happens, and it'll make a little more sense. It's something that I want to introduce just because we have to get some comfort level with that concept, because it throws a lot of people. The other thing to notice is that, remember, this voltage, this reflection coefficient is always described with respect to voltage. Actually, negative gamma describes the relationship between the reflected current waveforms. And so it makes sense, right? If I just looked at the current waveforms for an open circuit, the current goes down, and I actually have -1, the opposite polarity current comes back. So the current waveform goes down and then erases itself for an open circuit. That makes sense. There can be no current in an open circuit. There can only be current in the transient, as all those little inductors and capacitors charge up. Likewise, if you short circuit, then instead of a -1, you get a +1 here, and the current comes down. It's the current that doubles up. Well, that makes sense. You can have as much current as you want through a short circuit. Nothing's illegal about that. Okay. Any questions so far? Let's do an example with numbers. We introduced a lot of concepts here. It's good to solidify them with some numbers. Here's our example. So let's say we are on a printed circuit board with microstrip transmission lines. This is a PCB, printed circuit board. There's a ground plane on the bottom. And I got a conductive trace on the top that represents the top bar of my transmission line. It's 50 ohms because we always love 50 ohms in this class. And in reality, one of the things that you're going to see again and again is that we try to make our cables and our traces all to a standard 50 ohms, because if we're making our traces 50 ohms and people are given us surface mount devices that accept 50 ohms, they look like 50 ohm resistors at the end of the line, then we can minimize reflections. Not all components that you're going to buy off the web from the component catalog are going to be pre-matched to 50 ohms, but a lot of them are, and that makes a world of difference in terms of design. You don't have to waste your time designing matching circuitry and all this other stuff, all these other terminations. I'll show you how to do that. That's our next lecture, and we'll probably get to that at the end of this class, at least start it. Okay, but for now, let's say we got 50 ohm line. Let's say it's 10 centimeters on this circuit board, 0.1 meters. And we're doing some maybe emitter-coupled logic. One chip surface mount is connected to the input of another chip via this trace. And we got some emitter-coupled logic, ECL, which is a common form of logic that's used for high-speed interconnects. We're talking about the emitters being coupled on transistors on chips. And let's say that these are 5-volt logic switches. And so what we're going to try to show is what is the transient as I send a 5-volt logic source, logic waveform down this transmission line in an unmatched network. Because actually the equivalent circuit for this, my source resistance is going to be 10 ohms. And my load resistance, what this chip is going to look like to the circuit, is 100 ohms. And so here's my circuit model for the scenario. I've got 5 volts, source resistance 10 ohms. I'm going to switch it at time equals to 0. I've got a 10 centimeter transmission line here, terminated at 100 ohms, intrinsic impedance of 50 ohms. And let's see, transit time. Velocity of propagation for this problem is given at 1 times 10 to the 8th meters per second, which implies that the transit time is going to be about a nanosecond. Yep, nanosecond. So now what we're going to do is trace step by step what does the transient look like on this system. And before I even do that, I'm going to calculate 2 helper values that will come up again and again in our analysis of this problem. First of all, I have a load side reflection coefficient, gamma sub L. What is that equal to? Well, it's the load minus the intrinsic impedance, so it's 100 minus 50, over the load plus the intrinsic impedance, or 100 plus 50. It's a unitless value that is positive 1/3 in this case. This will tell me how much power or how much voltage reflects from that mismatched interface on the load side of the circuit. Now, you'll notice that I actually have a mismatch on this side. In fact, transmission lines are symmetrical devices. Symmetrical devices, which means I could just as easily describe a load reflection coefficient based on whatever resistance I have or impedance I have connected to the front side of the line. So for gamma sub S, my source side reflection coefficient, that's going to be, it's defined the same way, 10 minus 50 over 10 plus 50. So that's basically negative 40 over 60, or negative 2/3. So I have positive 1/3 reflection coefficient here, negative 2/3 reflection coefficient there. Does everybody understand that? Don't mind the source, you just worry about what the reflection resistance is on the source side. But you calculate your source side reflection coefficient the same way. This is just going to be the ratio of your new V plus to your old V minus as it strikes this interface. And now we can play tennis. We can look at the waveform go down and back and down and back and track how the amplitude decays over time and what the total output looks like at the output of this thing. If we find it's too distorted, if it doesn't look like a nice straight square pulse, then we need to slow down our circuit. Let the circuit die down, all of its reflections, so that we have a nice logic pulse, minus the stuff that goes on at the very front leading edge of the pulse. So really, in a way, a lot of times it's the transit time of the line and the amount of reflection on that line that you expect that will put the ultimate speed limit on the data that you can transmit. If you put your pulses, if you transmit at too high of a data rate, you got to put your pulses too close together, and you can't wait for all these transients to shake out of the system before you do a logic read, so to speak, before you do a state change at your next device. So let's do this. Okay, for t is less than or equal to 0, this is an uncharged line. Voltage and current, no matter where you measure them on the system, is 0. The interesting thing happens when t is greater than 0. And if that's the case, remember, I've got a 5-volt source with a 10 ohm source resistance, and I can use this equivalent for my transmission line. It's going to look like 2 dead Z0 resistors. 50 ohms in this case. That's correct. Let's go ahead and put that 1 nanosecond. So then we're going to change to this next state. This is 100 ohms on the load. So at t is greater than 0, I got a voltage divider here. And this indicates that I'm going to start sending, if I do my voltage divider correctly, my initial voltage traveling down the line is going to be equal to 50 over the sum of these two, 60, times my 5 volts, which should be equal to 4.167 volts. So that is the amplitude of the wave that initially starts propagating down the line. It's got, as soon as you connect it to the circuit, this is the voltage that pops up on the front side of the line. And since there is no reverse propagating current yet, it can only travel down the line in the positive direction. Yeah, that's right, voltage divider. 50 over 10 plus 50 times whatever the source voltage is there. So 4.16 volts traveling down the line. And that's pretty much it. I still don't see anything on the far end of the line because there's nothing over here to excite it yet. But when I get to 1 transit time, between, say, 2 nanoseconds and 1 nanosecond, now some interesting stuff starts happening. First of all, I get a reflection. My reflection coefficient is positive 1/3. And so at this instant in time, my V minus is equal to my forward propagating wave times gamma sub L. In other words, the 4.167 volt waveform that struck the end of the line times positive 1/3 over 3. That's my reflection coefficient that I just calculated, which leads to a 1.39 positive voltage waveform that starts traveling in the backwards direction. So if I looked at the voltage on that line as a function of space, I initially saw this 4.167 volt waveform come to the end of the line. Now I see a smaller positive 1.39 volts added on top of it. And this travels back. So that the total voltage measured before after this waveform has passed is actually 1.39 plus 4.167. So my load voltage is also that value. V sub L is this plus this, which is actually 5.55 volts. Didn't I warn you ahead of time that this was going to upset some people? For a brief period of time, we have a voltage waveform that is larger than our source. Remember, it's cool though. Power is still conserved. Power is still conserved. If you did V squared over my 100 ohm resistor, I would find that is less power than is actually carried down, which would be basically V squared, 4.167 squared divided by 50. You can do that calculation to double check if you don't believe me. There's more power being carried down by the line than is being dumped into the resistor. But this is a lossless line, so in fact you should get some energy balance. The amount of power dumped into the resistor is going to be equal to the power carried down plus the little power in the reflected waveform carried back. Yeah?
When you did the B minus, why did you use like gamma L instead of like gamma S?
Well, because we're talking about this time window when we're after one transit time, so the signal has made it down to the load side and reflected off the load, but the signal has not yet reached all the way back to the source yet, because that would take more than 2 transit times. So the reflection is happening on the load side, and therefore we use the load side reflection coefficient. After it's in the next step, when the signal makes it all the way back to the source, that's when we use the source side reflection coefficient, which is a different value in this problem, because we got 2 different impedances hooked up to either end of the line.
Dr. Durgan?
Oh, yes.
This is Bill in Savannah again.
Uh-huh.
I'm going back to pretty much the beginning of this problem real quick if I can.
Mm-hmm.
You gave us a velocity of propagation of 1 times 10 to the 8th meters per second.
That's correct.
You gave us a transit time of 7 nanoseconds and a distance of 0.1.
I believe it's a transit time of 1 nanoseconds. Maybe my boardmanship was a little not. That should be a 1 nanosecond.
Okay, never mind. Thank you.
Oh, you're welcome. No problem. A typo. A Bordeaux. Yeah, I kind of make, this is how I make my ones. I put little serifs on them, as if I was drawing a font. Sorry for my sloppiness. Good thing is that there are really nice notes in your book, right? It's like decipher my cryptic runes that I put up here on the board. Okay, so now let's start at the window 2 nanoseconds and 3 nanoseconds. If time is between these 2 windows, then enough time has elapsed so that the reflection, the waveform that we started with, that we launched at t equals to 0, has made it all the way down to the load. A portion of it has reflected back all the way to the source side, source side, and there's going to be another reflection on top of that goes all the way down to the end again. So that's what the window we're talking about. The third window in which a second forward propagating wave starts propagating downward. So let's look at that. What we have here is at the instant time is equal to 2 nanoseconds, both waveforms have traveled down and back, and I have a total of 5.55 volts on the line. Which, keep in mind that if we're looking at a function of space, if you have an oscilloscope probe and you just hold it on the line, you can only measure 5.55 volts. You can never tell just by measuring a single point with scopes, by putting the ground down here and then the probe up here, how much of that is the forward and how much of that is the backwards propagating waveform. You got to have multiple scope probes along the side looking at the change as a function of time, change in position as a function of time, to get how much of that is forward and how much of that is backwards propagating wave. Because we know what's connected to this line, we can figure that out. We figured out that it was 1.39 volts coming this way, back to the source, and that 4.167 volts going down. But at time 2 nanoseconds, that 1.39 volt waveform strikes the source side, which is also unmatched and has a reflection coefficient of negative 2/3. So that means negative 2/3 times 1.39 volts is going to start traveling down in this direction. That value, and I'll call it V minus minus, because it's the second waveform that's traveling down the line. The thing to remember is that the first waveform is still there. It's a DC source connected to this thing. So this thing just keeps dumping voltage on there continuously. Nothing has changed. And now I've got a reflection riding on top of what's already there. So my V minus minus is negative 2/3 times 1.39, also known as negative 0.927. So that's 1.39 volts, our backwards propagating waveform, striking negative 2/3 reflection coefficient junction. And when I do the math in the Magic Professor calculator, where everything's calculated ahead of time, I get negative 0.927 volts. And so that's going to start propagating down this way, and it's a negative voltage now, which means when you add it up to what's already there, it looks like an erasure. So here, you're at 5.55 volts. Over here, you're at 4.63 volts. And that value will soon sweep across the transmission line at constant velocity. So then when it gets to the end, that's the total voltage that you see right before it strikes the junction. Yeah?
And why is it considered a minus minus?
Well, I denoted two minuses because remember there's a V minus already there. That's the first waveform that was dumped onto the transmission line. The DC source connected to it. We had a V minus minus, which was 4 point.
I thought it was B plus.
Oh, excuse me. You're right.
Yeah, that's right.
I got you now. Should be a V plus plus. V minus minus is the next step, right? When there's a second reflection at the end of the line. It's a really good point to bring up, though, because this is a switch DC problem, right? So you always have to remember that unless you pull off that switch, that original voltage is still there. It's still being dumped into the transmission line. And so everything that you add on top of it is a superposition. That's not true when you're dealing with short pulses. And that's in a couple units, we'll do some examples with short pulses. And in that case, your pulse, it starts and it stops. And sometimes the pulse is so short that the whole thing fits on the transmission line. In other words, it's shorter than a transit time. And you have to remember that in those scenarios, there is no accumulation of voltage. It strikes the end, it comes back, it strikes the end, and it eventually dies out because there's not that much waveform to go around once you get 5 or 6 reflections. But it's always just the pulse. These cases, in these types of DC switch problems, that's not the case. The voltage is always there unless you disconnect it. Yeah?
So I was trying to visualize this. So when you draw it on the board, you got two separate things.
Mm-hmm.
Say if it's the codex cable, is it just one cable that's there and it goes back and forth in that same cable?
That's right. So if we want to go for the cable example, you got the inner conductor and the outer conductor. And you can think of the top bar as the inner conductor and the bottom bar as the outer conductor. And it's really a voltage drop between those two that's traveling, and a current waveform that's traveling on the leading edge of that as well, that's moving down. And then parts of that are reflecting back and forth. Yeah?
When you have that V plus plus there, there's the negative 0.97. Did you multiply that by the reflected 1.39 volts?
That's
or
right.
the total voltage on the line?
We're just looking at the portion of, not the total voltage, just the voltage waveform, the 1.399 that struck the edge. All the other stuff we've already taken into account, so we don't have to worry about that. Yes?
So what happened in the case where the RS, which is 10-ohm in this case, is greater than the D naught? So we just continue adding on? Because in that case,
Yes.
Yes. If our RS was greater than 50 ohms, there would be a positive reflection coefficient. You would get an accumulation at that point. However, remember that our initial step would have changed too. If it was bigger than 50 ohms, I would have much less than 4 volts put on the line to start with.
You want to take into consideration the load voltage until you get back and do another V minus minus?
Yes.
Okay.
In fact, here's another useful construct. I'll go ahead and introduce it now. Whenever you're at the junction of these interfaces, whatever strikes the edge, whether it's a V plus, your first waveform that you put on there, or your second waveform, or your 17th waveform, your V plus 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 plus. We define the reflection coefficient to be V minus over V plus. Sometimes it's helpful. Some people like the helper variable tau sub L. And that's the transmission coefficient. So the way we would use this, we would say our total load voltage is tau times V plus. So this is the reflection. V minus is V plus times my reflection coefficient. And my load voltage is whatever strikes the end of the line times the transmission coefficient. And it turns out that these are related, of course. Tau sub L is really just 1 plus gamma sub L. That makes sense, right? Because whatever I see at the output of this transmission line is always going to be my V plus my V minus. So the ratio is going to be 1 plus my reflection coefficient. And again, this is a little bit disconcerting because if you've got a really small resistance on your load that's much lower than Z naught, then you got a negative reflection coefficient. 1 minus something is, a small number. And a little bit of that transmits to the other side. But in the case that we had, our initial voltage came down. We had a plus 1.3 reflection coefficient. So that meant 4/3 of the voltage was transmitted across the junction. A bigger voltage than what we started out with. But you can see, if common sense is starting to be broken, help is on the way. We have an erasure propagating down to kind of knock that thing below 5 volts. So how does this work? Let's go ahead and finish this off. At time equal, go over to this one. At time greater than 3 nanoseconds, but less than 4 nanoseconds, what has happened by 3 nanoseconds? My signal has traveled down. A portion of it has reflected back. A portion of that has reflected back. And now I've got 3 waveforms effectively adding up. 2 forward propagating waves, 1 backward propagating waves. And I've got a total 4.167 volts that has made its way all the way across the line. So at the instant of 3 nanoseconds, I could take my oscilloscope probe, drag it across there, and I would get a constant 4.167 volts. However, at that instant, my negative 0.927 volts has struck the end of the line. The reflection coefficient is positive 1/3. So that means now
should be 4.63 volts. On the way back.
On the way back.
Yeah.
We're quibbling over hundreds of volts.
I have, let's see, 4.163. Oh, 4.63, you're right. 4.63. Did my calculation wrong on my, or I read it wrong. Oh, yeah, it's right over there. Okay, 4.63 total at the end of the line, negative 0.92. And what is it that reflects back? It's going to be a third of this. There's going to be a negative 0.31 volts. So now another erasure starts propagating back. This one only a third of a volt high, practically. So that the level here that you see at the load side is 4.32 volts. So at time equals to 3 nanoseconds, I could have an oscilloscope probe at the end of my transmission line, and what used to be a constant 4.63 volts now ratchets down to 4.32 volts. And again, this thing travels down, reflects back, flips sign, and starts to add again. We can keep doing this again and again and again. What I'm going to do is now draw this voltage waveform at the load as a function of time. Since we know how to it's the same procedure again and again for all windows of time. We know how to do that now. Let's see what this thing actually looks like. So I'm going to graph load voltage, V sub L, as a function of time. So this is the voltage observed at the end of the line. And what did we say? Based on, let's synthesize all the results in your notes so far. For the first transit time, I saw nothing. And it wasn't until 1 nanosecond transpired, and then my voltage waveform jumped all the way up to 5.55 volts. For 2 more transit times, I saw nothing, no change whatsoever, because whatever waveform I reflected back took 1 transit time to go back to the source, and then a portion of that reflected back to the load, and that took another transit time. And at that point, I jumped down to 4.32 volts. And again, 2 more transit times in that elapsed. And it jumped up, and it jumped down. And what you would find is that the value that this thing is converging to is 4.55 volts. It goes up, it goes down, it goes up, it goes down, and asymptotically approaches 4.55 volts, which conveniently is the load voltage for this circuit. Basic voltage divider. If you calculate this out with a 5-volt source, you should get 4.55 volts. Who knew that the road to get there was so complicated? But this is the actual bizarre-looking transient that shakes out on the system to get to the familiar result from circuit analysis. Okay, next class period, we're going to learn about termination schemes and how to avoid ugly waveforms that may distort your logic signals like this.